We'll be continuing with the chapter on work and power. So, when we talk about efficiency, what does it mean when you're efficient, inefficient? Basically, it talks about remember in the conservation of energy that it cannot be created or it cannot be destroyed. So, it doesn't mean that the energy that you want is efficient and the others are just like the ones that you don't want, you can destroy them. Not exactly. Efficiency is the ratio of what's the useful work done over what's your total energy input. For example, if you have a car, you have chemical energy for it to move. So that's your fuel. So it's your chemical energy. You want your car to move. So that's your useful energy output. But let me ask you a question. What is your waste energy here? What's the energy you do not want, but a car produces anyways?
Sound energy.
What is it?
Sound energy.
That's one, but what's the
Thermal energy.
main one? Yes, thermal energy. Notice that your exhaust pipe
Thermal energy.
produces a lot of heat. So that's the kind of energy that we don't really want because our main point is to get the car to move. So your efficiency is essentially equal to what's your useful energy output, what's your useful work done over the total energy supplied to the system. So there's actually a neat trick that my physics teacher used to teach. Efficiency can never be more than 1 or 100%. If it's more than that, just check your workings again to see whether everything is correct. So it's to see the main point. So for example, you have motors, engines, human body. So what's your main point here? To get something moving. For example, I supply 100 joules of energy. So I have my chemical energy. They start moving the bike. But in the end, the bike kinetic energy is only 15 joules. So the others were wasted on stuff like friction, thermal, sound if it's really rusty and squeaky. So your efficiency, the one that you use only for the reason of it to move, is 15 joules. So out of 100, it becomes 15%. So what is power? Power is equal to your work done per unit time. So if someone does 1 joule of work per second, they do 1 watt. Power is equal to what? Let me just close this Zoom tab. All right. So let me ask, if a person, let's say, lifts a box of 20 newtons, he travels, let's say, 10 meters over a span of 5 seconds. How much power has the person developed?
40.
Correct, 40 watts. You can summarize power in the equation. Power is equal to energy over time. So your energy here would be equal to FD over T. Energy over time would be FD over T. You can also talk about the efficiency in terms of power. What's your useful power output over what's your useful power input? We have a question here. So the right here we have a diagram where a crane is lifting 100 kilograms of block of concrete to a height of 16 meters in 20 seconds. So if our power input to the motor is 1,000 watts, what's the efficiency of the motor? So we want to find out what was our useful power output, the useful one to bring this up. So the waste will be probably in these gears, in these frictions, in these pulleys. So 1,000 kg, because we assume that G is 10 for this case, if you want to use 9.8, do so unless the question asks you to use 10. So your work done is equal to your force times distance. So your force is 100 times 10 times 60, which is 16,000 in 20 seconds. So it does 800 watts, which means 800 joules per second to move this block down. Your input was 1,000 watts. So you will need to use 800 divided by 1,000 to get 0.8. So efficiency here would be used we express in decimals. But if you want to use efficiency in percentages, once you use this useful power output, multiply by 100%. So for the questions later, could I request that the answers be expressed in percentage?
Okay.
All right.
Yes.
Another trick
Yes.
question is that, let's say we have a frictional force and we have a forward force. So we have car on the right, which is going at a constant speed of 30 meters per second. Highlight constant, steady. What is our output power on the driving wheels? That's the thing. In 1 second, it can travel 30 meters. So I believe that you all know that Newton's first law, when an object is stationary or at constant speed, there's no net resultant force acting on it.
Yes.
Yes.
Have you learned the rule? All right.
Yeah.
So
Yeah.
whenever you see constant speed, you can deduce that our force of driving force due to the engine 700. So it's equal to 21,000 kilowatts. It is pretty rare to see that your power output is force times speed. And to be honest, I only saw it when I was in AS levels last year. So how do we derive force times speed is equal to your power? So remember, power is equal to your force times distance over time. But this is also equal to speed, or we call velocity, which is why P is equal to FV. This is quite useful if the questions do want to ask you in this form. Let's just do a select questions here. Let's try question 5. All right. Question 5, maybe Inzu can start first. A crane lifts a 600 kg mass to a vertical height of 12 meters in 18 seconds. So, in terms of newtons, we assume it's 10 right here. What weight is this crane lifting?
Uh, 6,000.
How is it worked out?
Mass times gravitational.
Correct. 600 times 10. So what's your useful power output? What's your power output? Because there's no input here.
Uh,
Is it 4,000?
Yes, it's 4,000. Because 600 times 10 times 12 divided by 18. FD over T. How about Alvin? Let's
4,000.
try a question about efficiency. So
Okay.
if you supply 5,000 joules of energy and an engine only does 1,500 joules of useful work, what is your efficiency?
Energy does one of useful work with each of its efficiency means is useful energy output over total energy input. 1,500 over 5,000.
Could you express in percentage?
So should be wait. 30%.
Good, that's correct. But where did the others go? The rest of the energy. Where did it go?
Waste.
Yeah,
waste.
what is it wasted as?
Thermal sound.
That is correct. These are just a few general questions on work power. So the most important thing here is to remember that P is equal to E over T. So the biggest challenge here is just finding out E. So when you have E, you just make sure it's equal to F times E. If you have a mass of 10 kg, always convert to your weight in newtons. So 10 times 10 becomes 100. So it's mgd over T. In some cases, please remember. Now that we're done with efficiency, let's talk about in general. Like right now, I'm in my room, I need the fan. So the fan uses electricity. We all use a lot of energy. We all need to use a lot of electricity in our daily household. The lights at night, switch on a cooking stove, and a lot of various things. So how is this energy generated? How is it supplied to households? How do factories meet? How do power stations meet such a high demand of energy to supply for everyone? So in power stations, let's just break down how it works generally. In power stations, usually use fossil fuels like coal, oil, or natural gas. We'll talk about nuclear reactors in a short while. When we burn them, it actually increases the temperature of this water, which turns them into steam. And in steam, once it becomes a high pressure, it actually turns turbines here, which will activate a generator and it produces electricity. There's a cooling station here, which condenses the steam back to water. So the cycle repeats and repeats and repeats. The thing right here is that energy can be so-called produced here because our fuel already had chemical energy in the first place. So if energy was not created here, it is also not destroyed here. It was just transferred from chemical to electrical to be supplied to our households. Just for an additional information, once you transfer them through cables, you will learn this later in physics. You also use a transformer to vary the current and the voltage output. For nuclear reactors, it's pretty much the same, except you don't burn your nuclear fuel. You actually usually use uranium atoms. So your uranium atom, let's say you have a nucleus here, once you split into two smaller atoms, or was it nuclear or something? You actually do a process called nuclear fission, which releases a huge amount of energy. Now, like mentioned, the specifics here are also not really discussed here, but it's due to your mass energy conservation, which will be learned later. So to summarize, we burn a fuel or we have a nuclear reactor, it releases thermal energy. So chemical, it converts thermal energy. You boil the steam. This steam causes the turbines to rotate, which causes the generator to produce electricity. And of course, we have our cooling station right here. So that it goes back to the boiler room again. The thing is that power stations do waste a lot of energy, especially in cooling water, the waste gases, and like mentioned, you lose a lot in turbines too. We've been trying to reduce our energy loss as much as possible. But like mentioned, if your energy is in thermal form, you can't use it all. drive the generators. So these are how power stations work generally. These are and categorized in non-renewable energy sources, in which will be discussed in the subtopic just down below. So let's try the first question. Maybe you can start with Charmin this time. What are four different types of fuels that we usually use in thermal power stations? The four examples that were stated on top.
Nuclear,
Yep, what nuclear in particular?
nuclear fusion,
No,
nuclear
no, that's the
fission,
process. That's the process. But what's the fuel? What's the name of the fuel used? What do we use?
uranium,
Yep, correct. What else do we use? The very common ones.
uh, uh, can you use plutonium also?
No, in thermal power station you can use coal, you can use oil. What else?
Natural gas.
Yep, natural gas. Next, maybe Yinzi can answer this. In a thermal power station, what do we use the steam for?
To
Which
spin
was
the turbine.
Yep, it spins the turbines, which causes the generators to produce electricity. How about what does the cooling tower do?
Uh, what,
Could you repeat again?
uh, mm, cooling tower,
Yep,
removing the energy.
no, it was mentioned earlier. What does the cooling tower do? It condenses something after the steam spins the turbines.
Condense the steam and then
Correct, it
come
condenses
back.
the steam. Correct. So, Alvin, now let's refer to this table on the right. We have some data about power input and also power losses in our boilers, in our generators, in our turbines, and also the power needed to run our station here. So, let's go to part A. Where's the most energy wasted? From where you can see in this table.
Most energy wasted is in the turbine.
Yep, in the turbines for both cases, you notice it's very significant. It's already half or over half of it, which also pretty much explains why your efficiency is only 35%, as stated on top. 35%. How about for part B? In what form is this wasted energy lost? Usually once you boil the steam.
Heat and thermal energy.
Correct, it is lost as thermal energy. For part C, let's do a little bit of working here. For each station, just state X and Y. What's your electrical power output and what's your efficiency? Your useful energy or your useful power output this time is your electrical energy. Your electrical power output will be your power input minus all the detailed power losses. Just subtract all your power losses in your reactors, your turbines, the generators, and the power to run the station. So let's say for X, what's your electrical power output?
2000 joule.
Could you repeat a little louder?
2,000 joule. No,
2,000
2,000
megawatts.
watt.
Yep. How about for part
Megawatt.
Y? For power,
1,500 megawatt.
1,500 megawatts, correct. So what's your efficiency? The electrical power is the power that is useful, the output that's useful. What's your efficiency for X?
%36.
36%. The more detailed answer, precise answer, will be 35.714, but 35.7%. Yep. How about for power station Y? What's your efficiency?
26.7%.
Yep, which will round up to 27%, which is the nearest one. All right, that's good. So let's talk about the implications of energy and this power station. So the thing is that when we burn fuel, of course we use oxygen for burning, it produces carbon dioxide and water. These are your waste byproducts. So for example, when you burn natural gas, you also release methane, H4. For nuclear reactors, it usually produces radioactive waste. So, for example, if you don't handle it well, like Chernobyl, the entire place is uninhabitable for at least tens of thousands of years. So, here are a few problems with pollution, this station. The thing is that power stations that use fuel can produce a lot of carbon dioxide in the atmosphere. So the thing is that it contributes to your greenhouse gases, which will trap more of the sun's energy and also increases your global temperatures in a phenomenon we call global warming, which is stated here. If you have noticed, our average temperatures, if you do some statistics, for the past 100 years have actually increased quite drastically. If you use low sulfur coal, you usually won't emit as much sulfur dioxide, but you still emit a significant amount. So sulfur dioxide here will actually contribute to acid rain. So SO2 will actually react with water to produce H2SO3. Now, it isn't sulfuric acid, but it's sulfurous acid. And the effect here is still significant enough to kill marine life. It's harmful to health. And it also wears buildings. For example, if you can look at this building, it's been pretty badly damaged by acid rain, H2SO3. And like I mentioned, if you do not store radioactive waste correctly or properly, nuclear accidents may occur. Of course, we have more renewable sources of energy which may not possess significant hazards. For example, we can use power from the water or we can use power from the wind. But the problem here is that if we use half a liter of oil from burning, you can produce a kilowatt of electrical energy, but you will need 5 liters of fast flowing water for this case. That's why they usually build hydroelectric sources from flowing waters in rivers. The good thing about this is that you don't need any cost for fuel, you don't need to pollute gases, you don't need to deplete resources. As mentioned, oil and coal, they are in limited supply. And as theorized to run out. I think oil is theorized to run out in about 40 years. The problem with renewable energy sources here is that they're very expensive to build and they usually do not produce as much energy as our non-renewable energy sources. So we have the hydroelectric power scheme and we also have the tidal power scheme and wind farm too. Usually in wind farms, you need places where it's really windy, so it's pretty difficult to choose your location. You want to set up wind turbines. Like mentioned, they don't exactly harm the environment here. They don't produce much pollution, and they don't possess a significant risk to the environment. But like mentioned, they do cost a lot to build and usually do not produce much energy. So a lot of people like to say that, oh, why not just swap to renewable energy? But the thing is that it doesn't produce as much energy to meet the demand for the world's, to meet the world's demand, for the population's demand, which is why we still need to resort to non-renewable energy. So enough yapping here. Maybe we can get Alvin to answer the first one. In a hydroelectric power station, what's your main source of energy? You can refer to this.
Main source of energy. But may I see the question?
All right. What's the main source of energy in a hydroelectric power station?
Um, Gravitational potential energy.
Yep. A dam, what does a dam do? Is it essentially kind of just blocks a certain volume of water from going through? Kind of. And usually once your water flows down, or if your water flows downstream, your gravitational potential energy will cause the turbine to spin, which will produce energy. This produces quite a lot of energy, but you need a lot of water and also fast-moving water, which is why you usually take the long, the wide, and very populated and widely used rivers with very strong currents. Which this one is more focused towards geography too. For tidal power, your dam is built across your river. So the flow of this water actually turns the generators. How about Shami, the next part? We have the data about power stations A to E. So A will be coal, B will be combined cycle gas, C nuclear, D wind farm, and E large tidal scheme. So for C, it says here is an efficiency of 25%. So what does this mean? 25%.
It is quite efficient.
No, what does it mean by the 25%, which means what is the useful energy output? What is it in the form of?
Um, um,
You can use the terms fuel energy and electrical energy. What does the 25% signify in terms of these types of energy?
the efficiency to transfer fuel energy to electrical energy.
Will be 25%.
Yes.
All right. How about Yinzi? Which power station here has a very high efficiency? Let's not consider these values here as they aren't stated. Should be pretty simple. Which one has the
Combined gas,
combined
combined
cycle gas? Yep,
cycle,
would be. How about which power station here costs the most to build? the tip here is to cost the most is check the build cost per megawatt output and check the power output in megawatts. So which one costs the most to build?
Nuclear.
Correct. Because nuclear here, no, sorry. Large tidal scheme will be correct. Because nuclear will be 6,000, but large tidal scheme is 24,000. Oh. Yep. So which is why renewable energy sources like tidal are usually more expensive. Or wind farms here, look at how less they produce. How about Alvin? Which power station has the high fuel cost per kilowatt hour output? Which means your most expensive
Highest fuel
fuel source.
cost means
Yes, which one?
means every time should be A.
Correct. Coal costs 5 arbitrary units per kilowatt hour output. How about for part E? Which power station here produces the most atmospheric pollution per kilowatt hour output? So just check the table for the final one. Which one?
Oh,
Coal. Correct. So there are some pros and cons to using renewable energy and non-renewable energy, but meet the demand for world's supply, only non-renewable energy can do that so far. So as you can see, why do these two power stations have no rating for fuel cost, no rating for atmospheric pollution? Because what's your fuel here for wind? The wind. What's your pollution? Nothing. The wind just drives the turbine and says goodbye. Or let's say we have hydroelectric dams. What's your fuel? Water. What happens to water? The water just passes it and says goodbye. So there's no pollution here. There's no cost for fuel, and you still can produce energy. It's just not a viable option for the moment. So we still need technology to advance to harness more of this energy. You still have stuff like solar, but these are more of energy resources. So like I mentioned, you have categories of renewable and non-renewable. But let's talk about the sun in the first place. How does the sun release energy? The sun actually has a very special process called nuclear fusion, in which this nuclei of hydrogen atoms, they actually push together to form helium. You might wonder, why isn't nuclear fusion available here? Why is it only nuclear fission? Because the sun, it's a really high temperature for this reaction to occur. The problem with hydrogen, the nuclear centers, is that remember that it consists of protons and neutrons. The issue is that both of them are positively charged. So if you try to bring these two positively charged atoms together, that's going to repel. But luckily, the sun has enough force because it's so dense at the center, and because it's so high in the temperature, it can overcome these repulsive forces to form your helium plus energy. So helium is also partially part of the reason why over time, over millions and billions of years, the sun will slowly expand. Enough yapping from this section. For non-renewable energy sources, you have the most common one, fossil fuels, coal, oil, and natural gas. So what would they form from? They actually form from plants or tiny sea creatures which lived hundreds of millions of years ago, not just millions, easily 360. So 360 million years ago, once they die, they actually fall to the seabed and then they keep on getting buried under layers of rock and sediment to the point where their energy is very concentrated. And of course, nuclear fuels also release a lot of energy here when the atoms are split. As you can see here, 1 kg of nuclear fuel can store as much as 55 tons of coal. But the issue here is that waste from nuclear fuel is very dangerous. They stay radioactive for a really long time. They're really expensive to build, and they're also really expensive to close and dismantle the end of their working life. So it stays radioactive for a really long time. Later on, you learn about half-life, which is the time taken for the radiation count to decrease to about half. So if you take something like uranium, for example, let me see how long their half-life is. 4.5 billion years. So if nuclear reactors, nuclear power stations do have a uranium leak, or they don't dispose the materials safely, it would take a very, very long time for even this radiation to cut down by half. So as I covered, we have a few renewable energy resources like hydroelectric, tidal, wind energy, wave energy, geothermal energy, which means the earth, like for example, hot springs, you can find them in Iceland. Solar energy, which is very popular. For example, the latest news that popped up is that King's College from the University of Cambridge actually installed solar panels on their rooftops. So they absorb energy from the sun, and they can actually use it to heat water, and they can deliver electric current when they absorb the energy in light. So the problem with solar energy is that if you are not in Malaysia, where sunlight is not killing you every second, you don't get enough sun. Like for example, if you're in the States, or if you're in Greenland, or if you're in Antarctica, it's really difficult to get energy. And also biofuels, for example, wood, alcohol from sugarcane, methane gas from rotting waste. But I think the problem with some biofuels is that they might produce some pollutant gases here too. So you guys can complete this question here. I think I will need to inform you of what happens after this, because we have not finished.